All right, we're live again for a Monday night stream with Shenzen I. Um, I think I'm just going to jump into some review of what we did last week and see if maybe we can optimize a few of those things. I did look at them a little bit after the last stream. It was little help. Wireless game controller. Let's look at what this was. This isn't bad. Okay, so we have X and Y connected to joystick. A and B are okay. So here's the situation where I think SLX, the SLX command can help. If I pull up the manual real quick, and I'll explain why in a second we should be using that. But here, I was looking through the manual, there's this SLXP. So we sleep until data is available to be read on the X bus pins specified by the operand. So this avoids us doing like a sleep loop, or synchronizing both controllers with the same sleep pattern, right? So here we have to act when there is input on the radio transmitter. And what I have going on here is I have both of them sleep and I pass along, so X0 here from the radio. I think I pass that along to the other side. Move X0 to act. Wait, what am I passing along to the other side actually? That gets passed on X3. Yeah, so we move act to X3. So we send the signal to both of these. And we shouldn't need to do that. And I think that can cut down a lot in our design costs. Like maybe we can do this with just one chip. Well, probably two chips still. But certainly we can. We should be able to use a smaller chip. Let's see. I'm gonna go back and create a copy of this and see what we can improve. Okay, so this is 8, 635 power, 19 lines. Right. So here, what we're doing, X and Y are simple inputs connected to a joystick. So those need to get passed along. They're full like scalar analog values. A and B are simple outputs connected to buttons. Now, I want to see how I handle the A and B. So A and B coming on P1 and P0. They are simple outputs. P0 and P1. So we test P0 and then we add one to the ACK. So we use the accumulator. So we add one for A, we add two for B, and then the values 0, 1, 2, 3, 4 will tell us which combination of those two are set. It's like I'm saying a different bit with either A or B. B being the ones bit, no, the 2-bit, and A being the ones bit. Okay, so let's pull this out here, this controller. It only needs to be connected. I think what I perhaps can do, if I want to shrink this controller down, we're already doing sleep logic on here. We could do the sleep logic on here. And we could start on one controller, receive the input on one controller, and then move it to the other controller. And then that's where we move what we calculate onto the other controller and then pass it back to the radio. So let's take out some of these wires here and make a new design. Or let's lay down the circuitry first. So this will need P1 and P0. These would need to be connected to each other. So I'll connect like X0 from here onto X1 from here. I need another bridge. Oh, whoops. No, that's not quite right. This needs to go down. We could do it this way. Sure. And we could transmit from here. So we read here, this sleeps until we have the button value. Okay, so the receive. Oh, what am I doing? There we go. And then the transmit. Okay, I think I'm happy with that wiring. I just need to connect this here. Okay. Great. So what's doing the receiving? It's still this right side. So let's copy that bit over. So we're always gonna sleep. If you move that to the accumulator, and we test on that accumulator, and then we handle these pins. So we know for sure we'll be handling the pin. So I'm gonna move that down here. Okay, so that's enough to handle that code, the AB code. So after that, we move the accumulator over to X1. Oh yeah, we're already doing that. Great. No. We want to move that to the other pin. So we're moving that to X0 to the other chip. Okay, I think that's fair. Now if you can squeeze in at the top. Well, we'll let us sleep here at the bottom. But at the top, first thing we're going to do is get our radio signal. So that's X1. Move X1 over to the accumulator. We're going to test on that accumulator. If it's negative 999, then we jump back to the start. I have half a mind just to put this whole block into a plus. So I could test if it's not equal to negative 999. Is it TNE? TNQ? Let me check the manual here. Our tests, we have test equal, we have test compare. No. Okay, well, we'll do it with a jump. So here's start. So test equal, accumulator negative 999. Otherwise, we jump to start. We don't have enough space. I'm wondering if I want to put the receive on the other instruction instead. Well, this has two values to move out. So that star can just fit on that line. That's fine. I'll just make it a little bit smaller there. Okay, so test equal negative 999. And if it's not equal, then we move back to the start after sleeping. I guess we should put the sleep at the front here. I don't really like starting with a sleep instruction, but let's get this working first. We can always refactor later. So if it is equal to negative 999, then we jump to S. Okay. Now, meanwhile, on this side, we're sleeping on X, specifically X1, for the button information. And then that button information goes... What's the packet order? Let's look at the verification here. Okay, first we send X and then Y, and then we send the AB combination. So we can just start by doing that. So move P0 over to X0. Well, actually, we should sleep on X1 first. And when that happens, we move P0 to X0, move P1 to X0. And then we just move the value from X1, move X1 to X0. Great. So that's very minimal, which makes me think like maybe we should move some of the logic over to this chip instead. I think that should do it. We'll give it a run. No, the values we're pushing in are wrong. So what values are we pushing out? Okay, so for the first few... Oh, we did get a -1. Let's look back at the specification information here. What signal are we awaiting? Are we awaiting a -1? We could just put that under a plus. Test that it is -1. In fact, I don't think we need to be saving it to an accumulator, do we? Yeah, we can just test directly. So test equal accumulator to -999. And if it is, then we sleep one and we jump back to S. Otherwise, you don't care what the value is. Oh, not accumulator. X1. Okay, so here we should be getting our first -1 in. So let's step and see that. Okay, in this case, it was not -999, so we're getting the values from A and B. So we add, A and B are both off, so what we're sending across is 0. So we send 0 to the other one. The other one's been sleeping, and now it sends our X value, P0, which is 63. Great. And we send 37. And then we should send that 0 that we got from the other side. Okay. Well, that looks fine. That still looks fine. Here we missed a value. Why is that? Let's reset. Okay, so this here was still fine. Yeah, we sent those values. And we continue to sleep. Oh, we don't have a sleep statement here in this case. Okay, let's try it again. Okay, we still want to break at the same spot. We'll go here. This is where things go wrong. Okay, so we get 100 from both of them. So the value here should be 4 or 3. Okay, yeah, the value is 3. That's what it should be. So we passed 3 along. And we are sleeping. This one was sleeping until that 3 was ready. So now we move out 40 and 56. Or 40 and 66, rather. Great. And we move X1, which is a 3. Okay, so that's still fine. That's not where we get an issue. All right, now here we're looking at A and B again. And this should end up with 2, because just B is turned on. So P0, that's A. So, oh, you know what's happening? We never set accumulator back to 0. So in this case, before we do all of this, we need to move 0 to the accumulator. And at this point, I'm going to change this equality test. I'm going to change it to test if it's -1. And that means we have the go ahead to do stuff, including this next test. Oh, but I don't want it to chain to that test. Do I even have enough room here? Should I actually just be doing that logic here? Because this logic just takes longer. It is a third value we need anyway. Yeah, I'm just going to switch these two. That's the most straightforward way to fix this. Okay. That should do it for me. So here, instead of SLX, we have our loop. So test equal x1 to -1. And in that case, we grab the values of x and y. Okay, and these are both positive cases. So instead of moving that to x0, so we're testing this from x0. And then we're going to move those to x1. And here, and then we sleep. We sleep regardless of what happens with the test value for this. Great. Now on this side, we don't need this test or the sleeps, because what we're going to use is a sleep x. So sleep, we're waiting for x0. And we're going to move x0 to our output, which is x1. We're going to do that twice. We don't need this jump command. We don't need this sleep command. Move x0 to x1. And then we reset the accumulator, move 0 to accumulator. And then we do these tests on the A and B values. And then we move the accumulator out to x1 as well. And that apparently just works. Great. Okay, that's much better. So it's too cheap. It takes significantly less power, and the code is simpler as well. So we're happy with that. The laser tag. I think I already, no. Yeah, I think I did visit that a little bit. I made it much nicer, but I don't want to just, I do want to show what I'm thinking here. Okay, right. The laser tag is the one that had a lot of inputs. And ultimately, what I did was decide just to use these triple inputs. I was able to fit on one chip. That's actually nice. I want to show what I was thinking though, as optimizing on this. So I think here is where I finally decided, okay, let's just do what they advise and use a DX300. At least on this part here. And this part, I'm using it to handle inputs on the left and the right side. I'm still doing it across two chips. And I think at some point I realized one chip just handles it all. Okay. I mean, I did like the simplification process of this, so maybe I'll let myself forget this problem and see if I can recreate it in the future as I improve my skills. Okay. I did want to revisit CoolDad though. Actually, did I already do pretty well there? Let's at least take a look. So what's going on here? We have a radio signal. And when that data packet is received, we pulse the LED. Red, green, and blue according to a pulse. Oh, and then the duration tells me if I should keep going or not. Okay, so right, the data packet comes in and we have 4 values. So first thing I'm doing is moving x1 to data and checking that's -999. And in the case where it's -999, there's no other logic that needs to happen. So we can just move all these RGB values. Data goes to, oh wait, right, if it's not -999, then the first value is actually R, which is why it's data instead of x1. And then we test if our duration is still going, and in that case, we move 0 to each of RGB to turn them all off. And we subtract 1 for the duration. Now I think so we can definitely improve power usage here to the peak. And one thing I'm noticing here, so let me just run this for a sec and then we'll pause. The sub 1 runs every time, even if the duration has completed. So we're saving duration in the accumulator, right? I think what we can just do, we can just test if it's 0, and if it's 0, we move those down, and then we stop subtracting. Yeah, we need to be subtracting if it's not 0. Actually, can I just put a minus here? So we stop subtracting once we've hit 0, basically. That's an immediate improvement. No, we can't do that. Okay, so if it's greater than, if the accumulator is greater than, then we still need to, oh no, this should be on a plus. And oh, this minus, this move 0 will happen as long as it's less than 0, right? If this keeps going down, we want that to just happen once. So let's do this. Test equal, when it's 0, we're going to set these values to 0. There we go. And if it's not 0, we subtract 1. Okay, that's better. I'm not completely satisfied. This test itself does not need to happen. So once it's 0, otherwise we sub 1. Right, so this test happened. If I could make this minus as well. It will cause issues. So I want whatever command is here to be such that maybe this can still be a greater than. So we only test if it's greater than in that case. And if it is greater than 0, well, we don't do these unless it is... No, I don't think we can chain this together. I feel like right after the stream yesterday, I thought of a nice way to simplify this. Okay. Okay, suppose we have an inequality test here that's 0. We only perform it if... Oh, you know what? Even if it's a negative 999 does come in, we do still need to do a test. So we'll leave that there. Right, when do we not need to do the test? Once we have already hit 0. So we can gate that on another test of... basically, whenever we put that value into there, we start doing this. We would need a second accumulator for that to work. Okay, exactly when it's 0, we move these all... We turn all of these off. We could do another test. If it's greater than 0, we sub 1. Yeah. And that test we wouldn't need to do if we were 0, I suppose. Okay. I should be able to get 391 though. But that is better. Okay, if data equals negative 999, we shouldn't need to do anything at all. So what I'd like is to have a test where this can be negative so that it also gets skipped. All of this gets skipped. And then this can turn it back into... Okay, suppose this is positive here. So... okay, suppose this is negative, right? So we had an actual value to work with. And in this case here, I would like this test to leave the signal negative in certain cases when we want to leave the signal negative most of the time. But we want to change to positive when that is equal to 0. So that's good. That's good right there. So let's say the accumulator is 0. Then this becomes positive. Oh, this only moves in the negative case. No. We want the opposite. We want to enable this. So once it hits this line, that's already going to be enabled, right? Which is to say it's negative. So we want to flip to positive when we don't want these things happening, right? So test less than 0. Yeah, if it's less than 0. Cool. And the sub 1 case. Yeah. Let's let the sub 1 run every instruction. Nope. Okay, maybe that's ambitious trying to put it all under that one test. So test equal, let's go back to testing if it's 0. And in this case, we move yeah, when it's positive, I'll move those all. But the test doesn't need to be performed except in this case. No, it needs to be performed every time. Otherwise, when that's negative 999, we will be moving things to 0 prematurely. Well, I know the I know the optimization is in there. I'm just not seeing it right off the bat. And I know I thought about the other. Okay, it'll come back to me. It'll come back to me. And when it does, I can share what I actually ended up changing. Am I sure about that though? Okay. Maybe this will come back to me as I'm working on another puzzle. I'd also like to get rid of this chip here, but I don't think that's just very doable. Because we need 3P outputs. I suppose that this could be a DX300 chip. Yeah. That could be a DX300 to cut some cost. How would I wire that though? Because I need more space if I'm doing that. We can go up this far. So that just takes X0 and moves it to P1. Hey, Zuno, welcome. Yes, back in the circuitry. Doing some optimizations. There should be... I thought about it after I ended the stream last time, and there's a nice way to put a conditional here so that we cut off a lot of the instructions that we're running here in this later half. But I'm not thinking about it right off the bat, so I'm at least adding this cost optimization here. What value? Oh, wait, you know what? We can't do this. We can't use the DX300 because we're sending an analog value, not just on or off. So this goes back here. What if I flipped the polarity of this here? Because what I want to have here is a test not equal. I guess what we could do is our test to move forward is that the data is greater than -999. Okay, so when you have an actual signal, we move those signals across and we save the accumulator value. This test, when does it need to happen? It needs to happen as long as this value here has been set to something with duration. Once it goes back down to 0, basically it needs to be the test of the accumulator needs to happen when the accumulator is, yeah, that's circular, so we can't do that. I think we have to test it every round, but I can live with that. Okay, once it hits 0, we move all of these down. Otherwise, we subtract. Now, this subtract can happen a lot less often. Subtract only needs to happen when it's greater than 0. Type greater than, so accumulator greater than 0, then we can subtract. Oh, we broke something. Once it's 0, we move the zeros across. And if an accumulator is greater than 0, we subtract by 1. So what is happening here that makes that mess up? We never sent these values down after a subtraction or after the duration ended. And why is that? Oh wait, this here should be a plus. Okay, we subtract the duration. Zuno, how have you been? How's your week? Oh no, that's still not good. So I would let this slide, but I know I can optimize this, which makes me not want to. Okay, let it go. Yeah, it's still solved. It's still taking too much power. This test, I guess, is happening way too often. I mean, sub 1 should happen as long as it's positive, but this second test here, yeah, like maybe this should perhaps be a range. The thing is, I only want to make these movements once, right? And as it is now, what does my profiler say? I think those are minimal. That's the minimum number of times I can move it, right? It's just whenever that hits 0. I went to the MIT Mystery Hunt this weekend, and there were a couple fun puzzles. So if there's interest, I might share some of the ones I found interesting there. Or maybe I'll say that for another. Yeah, I might share it. But maybe I want to visit that. There's still a puzzle from like 2 years ago that I want to revisit and share. I don't know if I want to prep something before I do that. But there was one that had an electrical circuit, and it did really cool stuff with the images. It had a really fun like riddle along with it. It's not just doing circuits. You're not just doing computer stuff. And I had another really fun problem that dealt with permutations, and it was secretly about like you had to know stuff about a Rubik's Cube in order to extract the final answer. So maybe I'll finish a puzzle here and switch gears to that. Okay, but in the meantime, this I don't want to let this slide. This test here, does it even need to happen when you have a negative 999? We certainly still need to sub. This test does need to happen because the duration keeps going down, right? The only time... Yeah, let's like step through these cases. Oh, what's going on here? Okay, now we're doing everything. And then we set a big value in accumulator. And we're immediately checking if it's 0, which is fine. And then we also check if it's greater than 0, which I guess... Yeah, fine. Because we want to gate the sub 1. Okay. Then we move to the next one. And at this point we should... I think we got a negative 999. Right. But we're still testing if that's equal to 0, and I think that's fair, right? We have to do that. So this isn't really waste yet. So I think the waste comes once the duration actually runs out. So in a case like this... Oh, cool, yeah, I'd like to see your side projects. I like it when people have side projects. I like it when I have side projects. If you don't have side projects, you're working too hard. Okay, so here the case, the duration is 2. So we do still need to keep checking them, right? So this is fair, the commands I'm running. I don't like that we're testing it twice. Maybe we can do a test compare. We'll see. Okay, but now the duration hits 0, right? And at that point, we move those values over. And we don't. Oh, look at this. So we don't subtract 1. And because we're not subtracting 1, it runs these commands anyway. This test for 0 will keep hitting 0, and then in that case, the whole point of putting this test equals 0 was that happens only once. So let's comment out this line. And I guess in the case where we're just subtracting every loop, okay, 400, not bad, not bad, cool. I think that's all I wanted, wasn't it? I thought I tried this earlier and I was not happy with the results. Yeah, well, we keep subtracting 1 no matter what. And we keep doing that test no matter what. But these 3 commands we only hit on the one time that hits 0, that those all hit 0. Okay. This test here does not need to happen. I'm going to change this back here, this test equal. And I can think of a case when this second test doesn't need to happen, and that is when we are first setting this, right? So if that is positive, if it is equal to -99, we don't need to do that test. Well, no, we'll end up doing that. Nah. Okay, I'll live with 400. I don't know how I got 391. But at least I know I can do it. Let's go to an actual new problem. Okay, back to the story. So there's an unknown optimization device. Create a working design for this product to view histograms and leaderboards. Oh wait, yeah, that's just under everything. Unknown optimization device. So, device 2827. Poseidon 779, a decentralized autonomous corporation, has determined that thorium mining operations can be optimized by as much as 2.7% by creating a device with certain specifications. Okay. The specifications are included in this communique. Please create 50 of these devices and ship to 101. Oh, that's a long address. Payment will be forwarded upon verification of completed work. And this is from an unknown email. What is this? A decentralized autonomous corporation. Oh, it's a DAC. Like a crypto Ethereum corporation. Is a company run without human involvement. It has money and investors, but it makes decisions for itself on what to do with the money using information from multiple lower-level monitoring and analysis programs. Some of my classmates were studying them when I was at Princeton, but lately the hype died down somewhat. I guess they're still operating now, maybe even doing well. I'll do the job for it and see what happens. Okay, yes, but why is the computer corporation mining thorium? I made a copy of the specifications. It is sent. It is on your desk. Okay. All right, let's just do it. We're just doing our job. Okay. X and Y are simple inputs connected to an unknown device. Okay. It's presumably some sort of precision center. Power is a simple output connected to an unknown device, presumably some type of motor or high power switch. Map the XY coordinate to the corresponding power value as specified in the geometric specifications, which can be found at the supplemental data section of the manual. Oh, from X and Y we're getting quite complicated output. Okay. Wait, what's it called? This Poseidon 779's geometric specifications. Thorium reactor custom LCD. Are they gonna make a thorium reactor? They're going nuclear. Where is it? Poseidon 779. Wait, is this it? No. Here, 2827 geometric specification. Okay, so this is a geometric visualization of a state space. The 2827 actuator control must take a value as shown in the specification, dependent on the inputs as described. Okay, so if x is less than 20, we do 30 no matter what, I suppose. And if it's x is greater than 60, unless we're in these particular cases. Okay. The zero value in the middle is required so that the actuator avoids the flux point. We need to avoid this danger point. All right. Create a device that maps given coordinates. Okay. Well, this doesn't seem that complicated. So for y between, if y is between 40 and 80, we have special cases to handle before dropping down to this here. So first thing we handle is x is less than 20. Okay. Let's handle that. I'm gonna put on a big chip until I know I have enough space to put on a smaller chip. Oh. This does take 2 inputs and 1 output. I guess I could use 2 chips. You can't use a DX300 here because it's not, it's an analog output. Okay, so you have to use a minimum of 2 chips. Okay, and for now, this will sleep on X0. Let's see, let's put this over here. And this chip here can be pretty straightforward. Sleep on X0 and then move X0 to P1. Okay, so first you get the X value, which is going to be from P1. Let's see, we could test less than P1 is less than 31, I suppose, right? Because it says less than 20. P1 is less than 20. In that case, we move 30 to the output, which is X3. Okay, and we don't need to do anything else. Well, I suppose we could put a jump here. Yeah, for now we'll do it simple. We'll call this the end. And here we'll just have a sleep 1. By do it simple, I mean we'll just put a jump statement after this. I guess chaining these commands is kind of weird sometimes. You can't really nest properly. Okay, so there's that. And now otherwise, we should first test if y is between 40 and 80. So y is greater than 39 and less than 80. Greater than or equal to 40, right? 40 to 79. So we're going to test test less than 39 to y, which is p0. And to do an and, we just put a plus in front of the next test. So test less than p0, 80. Okay. And in those two cases, hey there, how's it going? Master Programmer Elemental, well, welcome. Yeah, we're doing some assembly and some circuitry. We're wiring together electronics. In this case, it is apparently a computer system wants us to make chips for their thorium reactor to make their thorium mining more efficient. Okay, so in the case that both of these are true, then we need to check if we are between 40 and 80 on the X. And then in one case or the other, we'll be 50 or 80. Okay, I'm just gonna copy paste this. Oh, my dog. You know what? I want to line up the P0s on one side. So P0 needs to be greater than 39, yeah? And it needs to be less than 80. And here, P1 greater than 39, and P1 is less than 80. Great, I think we have some redundant checks here, but we can refactor that later. So now, in this case, oh, I don't know where this line is. Greater than or equals 60. So if it is less than 60, we do 50. Okay. Otherwise, 80. So test less than, and it's the X value, which is P1. If it's less than 60, then in this case, we move, 50 out, move 50 to X3. Otherwise, and I don't like putting this minus here, because any of these failing drops us into this minus case. I suppose we could save something into an accumulator. I suppose we could save a value saying that we are in that square. So in all of this case, I don't know, we can move 50 to the accumulator. Yeah, we can move 50 to the accumulator to say that we're in a square. And then after that, we just look at this and we add 30. No, in this case, we actually stay 0. But now, depending on the accumulator value, yeah, it's just that we're chaining so many of these commands. We're gonna have to figure out how to write efficient conditional logic. Okay. any of you can think of the efficient way to write this, then I'm all for it. So this tells us we're in a box, right? We'll just move that to the accumulator. Now we can do another AND test. So if we're in the box, but greater than 60, then we move 50 out. I think maybe we shouldn't do the whole box. Perhaps we just do one little rectangle here. So we look at if x is between these two values. And if so, we then also check if it's between these two values. And if so, we do 50. Otherwise, we can just do 0 altogether. Okay, let's do that instead. So P0 was our y value. P1. So if x is between 40 and 60, less than 60. Yeah, great. And if it's also the case that y is between 40 and 80, test greater than, so P0 is y. P0 to 80. If all that is true, then we move 50 out onto x3. Otherwise, we move well, here's the thing. As soon as we fail this 60 line, we're going to move to this line, which is the move 0 out to x3. I think I need to do the same thing I did here earlier. Like, this is super simple logic, but if I'm going to fit it on one chip, this is a game. Shenzhen I. Shenzhen. Oh my god, Midnight Simon is back. Hey, how have you been? I haven't seen you in ages. How was your move? What is poppin'? Well, hopefully this assembly here. Yeah, so this is a game about coding in assembly. And we're designing like electronic circuits. And here in a little bit, so this weekend I just spent at the MIT Puzzle Hunt. And here in a little bit, I was thinking about going over some of those puzzles that I enjoyed there. You have a new streaming studio? Oh, I gotta stop by your stream and see what's going on there. Q Ultimus, it's been a while. I see Black Deep, good to see ya. Oh man, I'm excited you're back. Oh, welcome, welcome. So here, this is what we're implementing here, which is pretty simple, especially if like you have if-else statements. But the logic here, the conditionals work. The conditionals are weird in this game because what happens is you do a test, and when you run a test, it flips basically the plus or minus state of the whole chip. So like, I know. this line here, this test greater than P1 to 39, right? It tests that our X value here is greater than 39 and all of these flip. So you can't really nest conditionals because every conditional test you do after that is going to keep changing the values, right? Let's say I didn't want to run this conditional and I had a minus in front of it, or I don't know. Let's say this conditional gets skipped and another conditional is only supposed to happen after that runs. Well, then now that conditional will run anyway, right? So there are a few things I've learned is that if you want to do an AND operation on these, you can do a conditional, a test here, and then put a plus in front of the other test, and then now put a plus in front of this, move 100 to ACK or whatever to that register. And this line will only happen when those things are both true. Is that an AND? Yeah, right. If it's negative, it'll fail here. If this condition fails here, that will turn it negative. But here's a more interesting one to wrap your brain around. Let me just delete all of this here. If you have a minus after another test here, this becomes an OR. So that means like coming in, maybe there's no value that is not positive or minus, right? You come to this test, that's an opportunity to turn it positive and run this command here. Otherwise, let's say that fails, then this minus here means this second test will run, and that's another chance to turn it positive. So this is how you do an OR condition. So you can chain conditions together, but you still can't nest them, which makes something like this that looks really simple a little bit trickier. Like maybe I just haven't learned a trick yet. Time to start thinking in jump tables. Yeah. Yeah, we can't really nest, so we do need to jump around a little bit. And I don't know, like you could just put all the conditions for something to happen in one big nest. But you'd have like 4 of those statements in front of each one, and then you can't have a minus. And that's what I was just realizing a second ago, was you can't have a minus case because anytime one of those conditions fail, then you just fall into the full minus case. So I could have a test that checks if we're in this box, and then a smaller test does one of these two. And I could jump to that test, and from there, after that output, no matter what, we need to jump back to the end or back to the start. And if we're not in that test, then we have to do we have to choose between these two here. And perhaps we're forced to use 2 chips anyway. Perhaps so that I have enough space to write my code, I distribute this logic between 2 chips. And I have a special value here that means do that test or whatever. Anyway, here at the end, I'm going to put a label here, and we're going to sleep 1 and go back to the start. And before I refresh this here, I think I want X to be P0, just so that my brain doesn't break as much. Yeah, we'll make X P0, and we'll make Y P1. And the output can be X3. It's just, I have to think of them X and Y in that order. Okay. So first thing we do, let's check if we are inside of this Y box. And if so, we check this range here. So test greater than, we'll test that our y, which is p1, is greater than 39. And that it is less than 80. And then we will test if x is greater than 39. I think it's the same kind of thing. Yeah, greater than 39 and less than 80. P0 is greater than 39, and test P0 is less than 80. And great, in this case, we are in that box. We want to jump to, we'll call this like, we'll just call it like I inner. So we'll put this I label here and have a simple test that will end in us just jumping to end. Or could we just put the test right here? Well, here's the thing. If any of these tests fail at all, we want to do something else. And that is like do another, we want to do another kind of a test for like the outer box or something. Okay, yeah, we'll just call that O. So inner and outer boxes. And like maybe I can put, yeah, I think I have to do, I'm gonna go ahead with this, and then hopefully I'll be able to explain why that's necessary afterwards. And then maybe it's not necessary, and we can just simplify things. But for now, so we're checking on the inner. So I means we know we are in the inner box already. And when we're in the inner box, all we have to do is check if x is less than 60. So if x is less than 60, then we output 50. So test less than x 60. And if that's the case, move 50 to our output, which is x3. Otherwise, we move 80 to our output, which is x3. And can this just go here? The reason here, so this has a negative statement here, right? If I were just to put this whole thing in the positive with like the positives in front of it, let me just show. So if I deleted this and I didn't have the jump I, then this test only would have to happen when it's positive, right? And then we'd move to 80 no matter what, as soon as it failed the test that we are in the small box. So I have to have that jump because that jump stores that information for me. And here, after all that, we jump to the end, no matter what. Okay, we are running out of space though. What I could do, actually, I think I can remove this jump I. Well, hold up. No, I think I do have to keep that jump I, because that's be gated under the positive. Okay, so we have an O case. And it's the same kind of test, S less than P060. But in this case, we are moving 0 or 30 instead of 50 or 80. So move 0 to x3. Otherwise, move 30 to x3. And then we go to E, which is sleep 1. Okay. So this gets almost all of the logic. It is missing this bit on the left. But let's run it, at least make sure that's doing that much. Okay. Yeah, so it's correct for everything else. Except this x less than 30 case. So where's the part where we're moving? I could also label this here. And I can jump to that label as soon as, what's the case? X is less than 20. You only really need 2 lines of code. You just need to figure out how to make room for 2 more lines of code. What if here in the negative case, we jump to O, but we don't need this jump to I because we'll just naturally fall into I, right? Okay, so you can remove that. If it's not in a small box, we jump to O. Otherwise, we perform a test. Good. So we shaved off 1 line. If we can shave off another line, then we'll have what we need. Oh, we can do an OR. So here in the minus case, oh no. Test less than, so P0, X is less than 60. If it's less than 60, we move. No, we can call this all part of the outer box. And I think we just need to check then. We can just check this range here. Check if X is between 20 and 60. Move 0. Otherwise, whatever it is, you move 30. Okay, I think we've got it. So we need a conditional here. S less than, if X is less than 60 or greater than 20. So we'll do a minus here. Test less than, or no, test greater than P0 to 20. I think that should be 19 or something, but I don't know. And if both those things are true, we move 30 to x3. Otherwise, we move 0. No. We move 0 to x3. Otherwise, we move 30. I think we got it. No. What's actually happening here? It is wrong. Hold up. So we're outputting 30 here in like this case, when we should be outputting 0. Let's check our 0 case. So our 0 case means X is less than 60 and greater than or equal to 20. I'll just make that an and. Oh wait, yeah. This is an and. Greater than 19. Right, in that case we move 0. Otherwise. Okay. Nope, still not quite right. Okay, so here's some place where we're getting that wrong. So here we should be in the outer box, right? So, oh no, this is inner box. Oh, so the inner box is taking over when we shouldn't. And we're outputting 50. Ah, the issue was not with this down here. Should we be in the inner box? So when it's 50 or 80, this is when we're in the inner box. So something went wrong here. We're checking that y is greater than 39 and y is less than 80. Cool. And that x is greater than 30. Oh. X should be greater than 39. No. Yeah, x needs to be greater than 39 and less than 80. Okay. There we go. That was our issue. Hey, it works. We used every line of code on that chip. Great. So someone's been able to do it cheaper. They probably did it by doing 2 chips, 2 of the smaller chips, and distributing across that. And fewer lines of code. But it is minimal power usage, so that's fine. I'm happy with that. Yeah. Yeah, I'll live with that. That's kind of pretty dense stuff to write. It's definitely a different way of thinking about your conditionals. Even TIS 100 does it differently. It's like jumps based on the tests. Anyway, on to the MIT mystery hunt. So let's share some puzzles there. Let me just pull it up. Give me a second here. The other screen. That's fine. And I'll leave. I suppose I could leave the Shenzen as background music. I like the weather status updates here. Rain, air quality very poor, drone activity heavy. Okay. Turning up the game music. Oh yeah, sure. I can do that. Thanks for that. Actually, give me a second here because I don't want to show things I'm not supposed to. So there's one about electrical circuits, which I'll pull up. And then there's one about permutations and Rubik's cubes, which I'll pull up. Uh, And in the meantime, I think I want have any of you used Logisim? Wait, what's my oh yes, Rubik's cubes, my fave, definitely. Because I used some Logisim for this. It was unnecessary, but it was fun. Oh, so Logisim, I used this back in college, and now the creator abandoned it, and so now the open source project is Logisim Evolution, which I haven't installed on this computer, I don't think. Yeah, we'll play a little bit of Logisim. It'll be fun. And we need the MSI. Okay, I don't think we're in danger of showing anything we shouldn't, so I'll show you what I'm doing here. Um, okay, right now, just, you know what, let me check if this is winget, um, nope, not logism, logisim. Oh, there it is. Okay. Okay, well that's happening. I'll show you the puzzle. So here's yeah, the Snake Course theme is still there. But I will reskin at some point. Um, I guess I do it based on the project. I like skinning to match the project I'm working on. So my Avena code color scheme was there for a while, my editor. Next big project, I'll reskin to match the color scheme. Okay, so here we have a circuit. Um, and this is all we're given. We're given a circuit, and we're given these images. And you can implement the circuit, and that's what I did. In fact, I transcribed this stuff. Give me a second. I'm gonna hide my screen again. I don't want to be sharing stuff I'm not supposed to. So I transliterated the circuits, and then oh, I'll have to pull up my worksheet. Um, and I started exploring around with this a bit. Like, is there, I don't know, like, is there a state where all of them are on? Are there states where their individual ones are on? So each of these images has a number associated with it, right? So here's 10, 4, 4, 3, 4. And like, what do you make of that? Oh, whoops. Here, let me show what I'm actually doing. So each of these images has a number. Like, what do you think that number might mean? I've already solved the puzzle, so I don't want to just walk the solution. But if you have ideas, I'd like to hear like what your thoughts are on that. I know it's pretty obtuse, right? Um, but we have numbers up here. So we have 1 through 7 on the left as inputs, and we have 1 through 10 on the right as outputs. Yeah. So this could mean output 10 bits. It could mean like we want only number 10 to light up. It could mean we want all 10 to light up. Um, and the fact here that this has a 4, these have a 4, uh, those wouldn't be unique, right? So it doesn't mean like only light up 4. It probably means light up some combination of 4 of them. The numerals look low? What do you mean? Yeah, these here are pretty low. Um, so let me pull up some code and we'll do a worksheet. We'll call this circuits for 10 bits. Oh yeah, yeah. Yeah, I don't think they are just bits. Okay, so here are the circuits transcribed. Oh, I didn't come prepared to show these. And you can verify that. What I'm gonna do is I'm gonna turn this into code that I can actually run. Um, so I'm gonna turn first I need these to be variables. So I'm gonna turn all the numbers. So like 1, I'm gonna replace with P1. So those are just variable names now. Oh, oh. And then we are gonna replace 2 with P2. 1, 2, 3, 4. Okay. And we're gonna replace 3 with P3. And then we're gonna place 4, P4. And 5 with P5. Oh, I suppose I could change my stream title. Okay, we're now doing MIT Mystery Hunt. And then same for all of these. So 6 with P6, 1, 2, 3, and we're gonna do it with 7. 7 with P7. I'm sure there's like a regular expression way to do this too, but that'll work for now. So these are all of our logical statements for each of the 10 outputs. I'm gonna put those into a list. Yeah. And we want comma separated. Oh, yes, thank you. A little bit too late now, but I appreciate it. I'm not sure how to do a regex find and replace in VS Code. When I was in Emacs, that's like something I did on the daily, basically. So I should figure out how to do that. Okay, and then we are gonna make a list of inputs. Zede Shah, hey, welcome, welcome. So you caught me just as I was changing gears here away from Shenzhen. But now we're going over a puzzle I enjoyed from the MIT Mystery Hunt over the weekend. Um, so I'll give you a quick tour. There's not much to it. We're given this circuit diagram with 7 inputs and 10 outputs. And then we're given just these 5 images, right? And each of these images has a number in parentheses next to it, 10, 4, 4, 3, 4. Is it Let's. I don't. I think you have to be on a team in order to view this, right? I think you have to log in. I'll share that URL anyway. You could try that. This whole the whole theme of the puzzle hunt actually was pretty cool. Like they made a whole like Pokemon clone, so it's like it's Puzzlemon. It had like a world map. It had like I there's like a game world you could walk around in, and the puzzles were in each of these. There were lots and lots of puzzles in each of these zones. There were like all these zones and dimensions and whatnot. Um, yeah, it's pretty cool. I put a lot of effort into it. It is super cool. If you can get on a team, I recommend it. Uh, it's not like very programming heavy. So like there are very few problems that are like programming worthy, but this was one of them. But you know what? Maybe I can at least share. Okay, let me try to open this in a private tab. Oh, okay, I can share these assets in a private tab. So here's the circuits. And you know what? I'll share the first image. There you go. So you can at least see those. That first one basically is the puzzle. Um, okay, so we need to give values to these P's. So P1, and this is just me like kind of brute forcing. So list true false. Oh, it knows exactly what I want to do. Exact. And then we're just going to yield the list of outputs. Great. Yeah, that works. So these are like all the possible states. Val states equals that. Now from here we can brute force stuff. And I'm curious what your instinct tells you. Like, what's the first thing you'd want to brute force if you're looking at this? Because what I went straight for is oh wait, I think we want to save also the inputs. Um, let's do ins equals yeah, we'll have this return two arrays. So, or two lists. So val ins equals list of P1 through P7, cool. And then val outs equals that. And then what we're going to return is ins and outs, exactly. Okay, so first thing I'd want to do is I want to see if I can turn all the inputs on. I think that was kind of my first instinct. So we could look at states.collect. So we have case ins and outs, and okay, Copilot's getting ahead of me here. But yeah, this is what I want to do basically. Um, if all the outputs are true, what are the inputs? What state gives us all of those being turned on? And we see here 0, 0, 0, 0, 0, true, true. So so basically 6 and 7 are on. And that gives you that image of Josh Campbell from Drake and Josh. Um, or I'm getting ahead of myself. Like I'm turning all 10 of them on, and I'm assuming that's what the 10 means, is like it's related to this image somehow. Let's see if Logisim is finished installing. You have to know who the fuck the kid is to solve it. I didn't know what this image was about. I recognized the image, but even then, so what I have to do when I solve this is like I go there and I take a screenshot of the kid, and then I go to Google, and then I paste the image there and do an image search. 90s kids remember, yeah. Okay. The person is in the image is Josh Peck playing his character Josh Nichols from Drake and Josh. The specific scene is widely recognized internet meme, featuring the catchphrase, "I do not control the speed at which lobsters die." Okay, so now we've seen a couple other images of the lobsters, right? So what's if that's stirring anything for you, I'll let you say it. And in the meantime, I'll get Logisim up and running because I want to show you the circuit as well. So file, we're gonna open from my downloads, I suppose. Okay. Oh, sorry for your eyes. This is bright. I haven't messed with the settings here yet. Okay. So according to this here, if we turn on 6 and 7, that turns on all 10 lights. I think it means we should solve in Rust and set Scala. That might be true, actually. Um, Everything becomes crabs eventually, right? Um, yeah, I'll let you keep thinking about that. And what I'm gonna do here is make a nice, pretty printer for this. So let's def a binary string. Um, so we're given what do we want? Bits, list of Boolean string. Great, Copilot knows exactly what I want. So we're going to output here instead is BS for the inputs. And then we'll do a for each print line. Okay. And at this point, I'm gonna start getting to spoilers here. So these images all have something to you'll notice here. Phrase I do not control the speed at which lobsters die is exactly 10 and let 10 words long, right? So what that might tell you is that like, oh, this circuit turns on those words and makes a phrase. So I'm gonna write this a little bit differently. So instead of if outs, I'm gonna do if binary string for outs is equal to 1 1 1 1 1 1 1 1 1. Okay. So if those words are controlled by those inputs, and what other kind of phrases can we make? Right. So I'm gonna put this in here as labels. So this is gonna be I do not control the speed at which lobsters die. In fact, I haven't seen that scene. Let me, I can honest, I do not control the speed. I don't have the context for this at which lobsters die. I think I need more context for the meme. Okay, well, it's a meme. Oh, here's the original scene. Yeah, so let's play with this. And what kind of other phrases can we make? Um, I do the speed which, or I don't know. I do control the speed at which. Anyway, messing around with it like this isn't really gonna get us too far. So I'm gonna go back here. And can we think of a phrase that goes with each of these? So here, this one looks pretty straightforward. So this is an image of a speedometer. with a no in front of it, like a so that's like no speeding or do not speed. Uh, so what I would then do here is let's try and make the phrase do not speed. So these bits, I is going to be 0. I do not control the speed at which lobsters die. So this is the output that would say do not speed. So I'm going to run that through there. 11010. Okay, so back to Logisim. 11010. Wait, what? 1101011. And here we have something do not speed. Okay, so we have image 4 then. So do not speed, and this is number 4. And we can just call this number 1. Number 1, I do not control the speed at which lobsters die. Here, there's a Schrodinger with a lobster that could be dead or alive. So we could be like, do the lobsters die, or does that lobster die? That seems reasonable. Let's see if that's possible. So number 5, we'll try, do the lobsters die? So I do not control the speed at which lobsters die. Do not control the speed at which lobsters die. Do the lobsters die? So let's try that. And I'm going to move this over. Hang on a sec. And what we had was, so it is possible, 0110101. And in the real problem, what I did was like I actually went through like lots of different possibilities. I tested if it's possible to turn on just one output, and you could only do that for output number 6, right? And then eventually we got to this. So do the lobsters die? 0110101. So that is possible. 0110101. Do the lobsters die? This here is an undead character from Dota. So that one would be I do not die. So we'll move through these a little bit faster. So I do not die. And in this case, I do not control the speed at which lobsters die. So we'll try that. And there is one for that. Great. And then we have Lobster King. Okay, I'm gonna have to think about this in a little bit. There's a lobster monarch. I might have to Google that. No, it's clip art. I don't think it's a specific reference. He would control. Yeah, I do control. That's not a bad. That's not a bad idea, actually. We could see if it's possible. I mean, I already know what is possible or not, or like I know what the answers actually are. I do not control. I do control would be that, and it's not possible. Okay, I'm gonna need help with this number 2 because I can't remember what it is. So I do not die is number 3. Let's look at our words. So can I zoom in here a little bit? Oh no, oh, that's how we zoom. I control which lobsters die. Is that another idea for I control which lobsters die? Okay, we could try that phrase. Um, so I control which lobsters die. So I do not control the speed at which lobsters die. And no, there's no possibility for that. Um, is this actually, you know what? I'm just gonna Google this because maybe it is something. So I'll plug that into Google image search. Um, paste. Nope. Hmm. I control the lobster. I control the lobster might be worth a shot. Oh, I control the lobsters because I'm the lobster king. Wait, is that what you're saying earlier? No, you're saying I control which lobsters die. Okay, so let's try that. I control the lobsters. So I do not control the speed at which lobsters die. And there it is, there it is. Okay, so we are able to get five 7-bit binary words. Well, what do we do with this now? Like the first thing we could do is try converting this to ASCII, except these numbers here are pretty big, right? There's like a pretty big range. We're going from 11 to over 100. So that's probably not the alphabet itself. So a 7-bit spread is too much, but a 5-bit spread wouldn't be. So what I'm going to do here, I'm going to give these all values. So we're going to call this image 1. So val we'll call it A1, A2, and I think we just want to collect first. We're just going to do like dot head on each of these. Dot head. So val A3 equals that. Dot head. Val A4 equals that. Dot head. Okay, so we have our 5 values, and we can try converting that to ASCII. I already know it doesn't work, but we can transpose. So we can take a list of all of those, list of A1 through A5, transpose. Let's look at what we have there. So we have a bunch of lists, so each of those lists will want to make string. Map. So the bits, we're going to do bits.makeString, and then we're going to parse that as binary into a number. So integer.parseInt. No, we want to parse int with a radix. Is that this one here? So we're gonna parse that string in base 2. Oops. Okay, so we have those numbers, and those are all less than 26, so that looks like that can be an index into the alphabet. Um, so let me keep going with that. We're just going to do a map minus, or let's see, what is it going to be, plus 96 or plus 65? Let's do plus 65. So n, do n plus 65 dot to char. Nope, I think we overshot because the a is going to be 0, so I'm going to do 64. Yeah, there we go. Um, and we get a string, bombers. And bombers was the answer to this puzzle. So that's what a mystery hunt puzzle looks like. So we have a lot of things like this. It was a lot of fun, very well worth the time. I'm on a big team, but it's pretty casual. We definitely weren't expecting to finish, but there were like, I don't know, like 10 teams that finished. It's a huge production. There were lots of people involved. Um, if you look it up on YouTube, you can find like the closing ceremony where they give all the stats and give like a recap of the whole thing of what the puzzle hunt was. And then I'll show this one briefly. What happens here? I won't do like a live solve of this, but here, this is basically like little crossword puzzles, right? So cat likeness. Mm, I don't know. You come up with some word, and then contents of the second stomach. So this is, I think one of these was dessert. Dessert, and I think it's okay if I look at this here. Yeah, so if you had felinity and finitely, so felinity was cat likeness, and finitely was the B clue. Um, yeah, so one of these is finitely, and you put them both here, or you put the B clue in here, knowing that's a permutation. You realize that it's the same letters as in felinity, and then you notice that between these two, just a few letters are swapped, right? And what you end up getting is like a permutation of these three corner pieces. So uh, I could show here, and Felinity, it's highlighted here. So the three corner pieces are rotated. And I think the puzzle actually clues you in about this being about Rubik's Cubes, maybe? No, it doesn't. Um, Here, let me solve this real quickly so I could show you. I don't think you've seen me solve a Rubik's Cube on stream yet, so here we go. I don't know if it's in camera or not. It's kind of awkward making sure the angle is right. Okay, so we've got a solved Rubik's Cube here. And what I want to show with this is that it's exactly that permutation where those three corners are swapped. And this is a common enough case that this algorithm actually has a name. And a bunch of these permutations of just the final layer, so everything else solved, but just the final layer corners or edges, those all have one letter names. So if you know those, or you could look up on a sheet of Rubik's cube solving, then this was A perm, this is the N permutation, and then this third one was a T permutation. No, is an R permutation, And here in the question mark, they have a +1. So you have AN, and you have to add 1. So it becomes S because of the T permutation. Um, and then that turned out to be ANSWERS. So like there's no W, but there is a V perm, and then you just add +1 to get the letter W. And the answer there was answers. So yeah, those were a couple puzzles that I enjoyed. I do wish there were more puzzles in there that were like kind of advent of code-ish. That'd make it a little bit more fun for me, but there's still like plenty of fun to be had. And this electrical circuits one was cool. Um, anyway, I think I'll do maybe another one or two Shenzhen puzzles. I had to look up the pronunciation. Pronounce Shenzhen. Shenzhen. Except it's not like right? One of these days I'll figure out how to pronounce all of these properly. If I'm going to be playing this game, I should be able to pronounce them. Shenzhen. 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 I'll say Shenzhen. I'll need to listen to it. Yeah. Yeah, I know. Um, so I'll look these up. So I'm not mispronouncing them all on stream. But I've heard pronunciation for this before. Figure it out. We'll figure it out. Okay. Oh, right. The responses to my having solved that. So this prompt here, um, we got this request to build this optimization device that makes mining thorium easier. It didn't come from a human though, so it comes from a decentralized autonomous corporation. And we were like, okay, well, let's just make it and send it off to them. So they respond, task verified, payment en route. What a future we live in, eh? That's cool. Yeah. Um, whatever they're doing with the thorium mining, we don't care. They paid us. So check my email. Undocumented instructions. Let's actually make this visible here. Oh, hold on. You've got the manual in my way. All right. So I was chatting with a mate at the pub, and it comes to light that those Chengshang microcontrollers we use everywhere have a secret instruction that isn't in any of the documentation. It takes the format of Gen P RIRI and conveniently generates a pulse on any simple I/O pin. So P is the pin. The signal switches on, then off for however many time units you want using the last two operands. So Gen P XY is equivalent to like moving 100 to P, sleep for X, sleep for Y. Oh, that is so nice. Bloody hell, I could have been using this all along and saved so many instructions. Jay, did you know about this? That's nice, actually. I want to revisit some puzzles with that. Yes, actually, it is in the documentation, the Chinese version. Just like the at conditional. There's an at conditional? The what? Okay, seems like many instructions are not translated yet. Putting an at symbol at the beginning of an instruction causes it to execute only once. Have you been initializing code? Okay. Well, that's nice. Cool. Well, maybe we'll have use for it here in this next device. Okay, the product, a token-based payment kiosk. To my fellow expats, have you gone to Three Kingdoms Land yet? I just went to the one in Shenzhen. The recreations of ancient Chinese society were extremely fascinating. You even get old metal coins and you have to use to buy things with, as if you were really in the past. I watched reenactors take my coins and then count them by hand. Isn't that bizarre? I thought they could use coin machines to count the money faster, so I negotiated a deal with them to build some here. Oh. Um, won't the coin machine be a little out of place in a theme park that's supposed to be a historical recreation? Carl, I already spoken to them about the look. The machine will have a beautifully carved faceplate design with dragons and heavenly mountains and all that stuff. It won't look out of place at all. The machine just has to know when you put it in the right coin total, such as the price of one thing. It rings a bell to let the person behind the counter know how to hand you your item. That makes change in real physical coins. It's really like bygone times. Okay, let's give it a shot. So there's a price. We have multiples inputs and outputs. That's more than expected, honestly. So in1, in5, and in12 are simple inputs connected to a mechanism that accepts and detects 1, 5, and 12 tokens. Okay. Bell is a simple output connected to a solenoid that rings a small bell when triggered. Okay. Out1 and out5 are simple outputs connected to a mechanism that dispenses 1 and 5 tokens as change. After a sufficient number of coins have been inserted, the payment kiosk should ring the bell and dispense change as indicated. This will be a use for our pulse command. Right, so this pulsing on the output on out1 is dispensing coins. So 5 and then the ones. Okay. So how do we know when the inputs are done coming in? I suppose as soon as we hit the price 16, then we ring the bell and do things. So let's pull out a microcontroller. Oh, hold on. We want a DX300 here. Just going to take all of our simple outputs and turn it into one X bus. Oh, you're fine dipping out. We'll catch up with the MIT puzzle in the pod. Yeah, great. Yeah, glad you like that too. Oh wait, no, you dipped out for a bit. Oh, okay. Yeah, it's an interesting one. Let me know what you think when you do get to that. Okay, so here, this will represent. So every time this value changes, basically, we add to like some counter. I'm just gonna start with the big chip. And we're kind of like counting pulses in, aren't we? Yeah, it's gonna be high for 1 second and then low again. And can multiple coins come in at once? It doesn't look like we have to worry about that. So in the case here, where we have 100, that means we add 12. So first I'm gonna set my accumulator to equal 0. Well, we can do that. We can do that at the end. So we're gonna test if our X input is 100. X0 is 100, and that means just the P2 bit is on. If that's the case, add 12 to our accumulator. And then we're gonna have other tests. So for X0 equal to 0, 1, 0, that means add 5. Add 5. and then test x0 equal to 0, 0, 1. And in this case, we will add 1. I feel like perhaps there would be a way to condense those. But we'll see. And then now, after adding a coin, we check if we have hit our price. So this price, what kind of input is it? It's an X input. I'm gonna put that down here as X2. And let's wire up the whole thing actually before we get too far here. So these things are only going to use 100, so I think I can use this chip here. So P0, a 1 is going to mean we output 1, a 10 is going to mean we output 5, and a 100 is going to mean we ring the bell. And we'll connect that to X3. Yeah, that seems like a reasonable way to wire this. We have everything we need. And bell. So we're pulsing multiple things at once. I don't think that the pulse command that we were just given works on... I think it ends up blocking. Right, if we went back to that, let me just check real quick. It's equivalent to move 100, sleep so and so many times. Yeah. So we're pulsing multiple things at a time. And in that case, we can't use this gen p command unless we use 3 separate chips. Which, you know, I guess we could. It'd make our life easier. So like maybe I'll start with that and then we can always optimize later. Okay. So now we test if accumulator is greater than price. Test greater than accumulator price, which is x2. And it's really greater than or equal. So I guess we have to do this or test equal accumulator x2. There we go. So that's an or statement. And if either of those is true, then we go to the output bit. I think actually we want a separate chip. What we can output here is the amount of coins that need to go. And when we're counting out coins, right, so this can be handled by one chip, because that's just pulsing. The bell can be handled by this chip here. So I will send, we won't use this. Instead, we'll use this chip here. This is starting to get in my way. I'm gonna move the clock, not the clock, the price over to the left side. Do I have a Twitter? No, not a Twitter. I have a defunct X account. No, I don't really use that anymore. I made a Blue Sky account, but I haven't really started using that yet either. But if you were looking me up, I'd be it's twosquared.com on Blue Sky. Okay, so we'll keep the price here. I don't use Kick, no. My socials are linked on my channel. What I do have... What do I have? GitHub, YouTube, LinkedIn, which is not... I have a Discord. That's a great way to get a hold of me. But as far as like social stuff, I'm on GitHub, Twitch, and YouTube. If you want to get me offline, Discord is probably the best way. So if I want my chip dispenser or my chip dispensing chip, my coin dispensing chip, so this needs to have P1 and P0 connected here, right? We can make that with a bridge so that we can access the X0, because the X here is going to be the amount of change that we're counting. This is going to be our first time using a... we've used loops before. And... geez, this thing really gets in the way. So we can send a pulse... I guess we could send P1 directly out to the alarm, and we can just pulse the bell. Right, something like that. We can put the price on X0, and we could put the inputs on X1. Okay, this layout I'm a little bit happier with. So now X2 can go out to the other chip, and P1 can pulse out here. Okay, we do need to change these though. So our input from our coins is now coming on X1. So we'll change those to X1. And then our price is on X0, so we're going to change those here. Great, now in the case that we have reached or exceeded our price, we're going to sub the price, and now our accumulator has our change. And in this case, we move the change out, so move accumulator, our change to X2, that brings it to the other chip. And then we're gonna pulse P1. It's gen on P1, a pulse of length 1, 2, 3, 4. And you only do it one time. Actually, let me double check that command again. Sleep X, sleep Y. So it generates a single pulse. Okay, so we can like sleep 4 and then 1. Yeah. So generates on P1 a pulse for how many seconds? The alarm, the bell? That looks like 4 seconds. Yeah. 4 seconds, and then sleep for 1 second, and then we start a loop. And if we're not doing any of that, we've not hit the change, then we're just gonna sleep for 1 second. Holy, yeah. Okay, so let's try at least the alarm. Oh, part not sleeping blocked on right. Oh, yep. We should actually read the thing from the other side. So here we're gonna sleep X on. We're gonna sleep to wait for X0, and let's just move X0 to act. We're not gonna do anything with it yet. but we'll see how much change is necessary, right? So 8 changes necessary, then 11 changes necessary. But the bell, is the bell working? Oh wait, after all of this, we should set the accumulator back to 0. Move 0 to the accumulator, because we have dispense change. Okay, so the bell is working properly. We just need to dispense the change. Okay, so we're gonna have a label for 5. And we're just gonna pulse the 5, which is P0. The number of time, or we can subtract from our accumulator until it's less than, right? So we're gonna sub 5, and if our accumulator is still greater than 0, then that was fine. So test greater than, accumulator greater than -1 actually. Then it was fine to output that. And in that case, we should send a pulse, which is gen on the 5, so P0, 1, 1. Otherwise, if that made us negative, then we should add that 5 back. And then handle the 1 case. Oh, right. When we do output a 5, we should also just jump back to 5 and keep doing that. Yeah? And then next is the 1 case, which you don't have enough room for. So I'm going to do another big chip. I'm going to keep writing here. So in this case, we do similar logic, sub 1, test greater than, we can just do a test if equals 0. So test equal to 0. And if it's not equal to 0, then we were fine doing, or you know what, we should put the test at the start. We'll have different logic in these two. I suppose in this one here, I could have tested if it's greater than 5 and put that at the start. So we're going to test greater than, we're going to test that we're positive. And in that case, we're going to gen on P1. Actually, let's wire that up first, so that we know what our pins actually are. We can delete that. Okay, so P1 is still going to be output 5. No, not still. P1 is now output 5. And P0, let's keep putting that off x0, is going to be our output 1, and we're going to use 2 bridges to get there. Okay. Great, so now this is on P0 that we're generating the 1 ticks. So gen P0, 1, 1. And then we jump back to 1. Otherwise, we are done. So we just sleep for, we just end. Okay. And yeah, so here up above, we were doing this thing where we add back 5. We don't need to do that. We'll just put the test at the start. So test greater than, accumulator test that's greater than 4, right? If it's greater than 4, then we can still do this. Then we sub 5, and then we gen P111 to actually output it, and then we jump back to the 5 loop. Cool. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 instructions. Could that fit here? Let me just check. I mean, this 5 would have to be on this line for sure if that's going to happen. Nope, it doesn't fit. Okay. If someone sees a way to shorten that down by 1 instruction, it will save me 2 yuan. Oh boy, we are doing a lot of subtracting. Okay, let's see what's going on. So we have... Oh, that's too fast. Okay, so at some point we have another 12 come in, so we're at 24, right? At 24, it is time to bring some change. So let's step through that. So it's greater than x0, which is the price, which means we're going to move the accumulator to x2. Okay, so this finally has a value, right? It has a certain amount of change that needs to dispense, which is 8. Yeah, 24 minus 16 is 8. Okay, then we check if our accumulator is greater than 4. It is. So we subtract 5, and we're now down to 3. So we send a pulse for 1 yuan. And we jump back to the 5 for another test. And in this test, we fail because 3 is not greater than 4. And then we test greater than 0. So it is greater than 0. Oh, we forgot to sub 1. I see. Yeah, we need to subtract 1. Oh, that's interesting. So here we output 5 and output 1 in the same loop. Why is that? All right. So here, what do we have coming in? We have add 12, we have 17. So we have 1 change to give, right? So we're going to subtract the 16. So there's 1 change. We pass that over. So we have 1 change to give. So in this case, we should just... Why is this output 5? Why are we supposed to output 5? That doesn't make sense. We only need to output 1. Oh wait, all of these values came in. So 1, 2, 3, plus 5 is 8, 9, 9 plus 12 is 21, minus 16. So we miscounted, that wasn't 17. Okay, so let's go, we'll stop here and look at what we're counting. Okay, so this comes in. And that brings us a value That's giving us a value of 1, right? It should. So this should fail. This one should pass. No, none of those worked actually. I think I want to move that to the data register so I could actually see what value that is. But P0 should be the 1 bit being sent. Maybe it can only send it once, and the first time we read it. No, every time. I wish I could see the value that was being pushed. Okay, let's just move it to the data register so we can at least read it. So move x1 to data. And instead of testing on x1 multiple times, we'll just test on data. Okay. Let's see what's going on here. So you move x1 to data. There is a 1. So this instruction should run and add 1. Yeah. Okay. And then we add another 1. Cool. We add another 1. Why is data being set to 0? When did data get set to 0? Oh, right. That's fine, because we're still adding it to the accumulator. So we have 3 in there. This should bring us up to 8. And then plus 12, or plus 1, brings us to 9. And then eventually we get to 21. Great, and now having 21, we send... Cool, that looks good. It must be the case that you can only read that value once from this DX300. Okay, hey, I'm firmly average there. You can't really do it in fewer lines of code. Someone was smart about power. But cool, I feel good about that. You can't really make it cheaper, can you? Let's see what people were able to get on the histogram. Someone was able to do it in 10, which tells me that they dropped 1 by not using this. But are there even enough inputs in that case? No. Oh, what that tells me is that they perhaps, instead of using 2 of these for 10, they used 3 small chips for 9. And each of those chips would, I suppose, be connected to an output. Huh. I feel like that would complicate things a bit. Oh, no, because the chips would need to read the inputs as well. Yeah, like 2 of these would go into 1 chip, and then a third would go into another chip. And I suppose you could express what? And you'd have to split up this logic between 2, 3 chips? I don't know. However you did it that way, it's probably complicated. Okay, I'm happy with that. I'm wondering if I can make at least a power optimization. We have to do each of these checks, right? Can we do fewer checks? Can we not check it 3 times? But we do have like 3 different cases, so each of those 3 different cases do have to be gated. Yeah, one of those 3 cases is going to be true. I suppose if this test here, if it turned out that that test was true, the others aren't possibly going to be true. So I could turn this into a minus here and not run that test, but then the add 5 would run. I guess it could be a jump. We jump somewhere if that passes. Then we don't have to do the other tests. I'd like to figure out a nice way to do a switch case here. And I suppose we could do that by chaining together those tests. Let me just play with that idea. Okay, so we can test if it's that, right? And if it is that, we could jump to 12. Otherwise, we test if it's that. Right, so in the positive case, then it won't also fall down to that case there. Yeah, I think this could work. So those all have like minuses in front of them. And then we jump to the 1 case. I'm gonna make a copy of this and just try out that idea. Okay. So we still start by moving x1 to data. Move x1 to data. And now here, it's just gonna be like add 1. And then in the 12 case, we add 12. And then we jump again. And the 5 case, we add 5. Then we have to jump to the part where we move things out. And then ring the bell. And I just don't think we're not gonna have enough room. Yeah, it takes too much space unless we move logic to another chip. Okay, well, it is worth taking a look at that idea. Maybe I'll leave this here as a reminder to myself that I want to explore that. And the result is a small start, but like us, this company has global expansion in mind. As it said, I need to translate that. Thank you so much for your ancient wisdom, David. You're welcome. Good enough for Chinese government work, exactly. Okay. Let's find a raid. Hey, Howling Fantods is on. I think a lot of us are part of that crowd, yeah. So let's go there. And as far as next week, I think I'll continue doing Shenzhen, Shenzhen, Shenzhen. But when I start doing other things, I'll let you know. It was nice to do that little detour with the puzzle hunt today. Oh, wait. There is something I do want to share. Let me see if I can pull it up. I want to show. I'll bring it up another time. Okay, next time I'm on, remind me because I wanna talk about some logic puzzles. A book of logic puzzles I really like. Um, that is secretly about. It's not actually just puzzles. It's secretly about functional programming. And like things like the Y Combinator, but it's like poses logic puzzles. It's like about self-reference and fixed points. Um, and it has a lot of logic of puzzles of the form like truth tellers and liars are talking about themselves. And it's related to like things I want to do and read. And like I've started reading Lean 4 and how that might become a project here in the near future. Um, I'll add it to the list of other projects I want to do on stream. But yeah, I want to share some logic puzzles next time. But yeah, in the meantime, have a good night. Let's enjoy some leak code with the Howling Fantods. Good to have y'all. What language needs better type system? Um, oh yeah, right. The fair enough. Okay. All right. Have a good one. Let me try to click this thing.